Hey, today we are going to look at what is RFC 1918 and what is this concept of private addresses. This is something that you would have encountered often when working with networking and when trying to connect different networks. So to understand that, let's start with what exactly is an IP address. When there are devices and machines and servers and all of this on a network, you have to have a way in which you can uniquely identify them. And the initial standard for identifying these machines was what is called an IP address, or is what is called an IP address. And the standard that was used today, it is referred to as the IPv4 standard. There is also an IPv6, a version 6 of which uses a different format, and it is continuing to gain traction. But IPv4 is still extremely popular. So when these machines are directly connected to each other, they can obviously talk to each other directly. In those cases when you don't have a direct connection, because these addresses are unique, the intermediate machines and servers that are going to route these data packets originating from the source and intended to the destination knows exactly where it is going to go. Right? So like you wouldn't have a duplicate phone number or a duplicate address, right? You can't have a duplicate IP address because then there would be a problem with routing. You wouldn't know where exactly this data packet has to be sent. Now, this IPv4 address uses a format like this. There are 4 numbers separated by dots. And these numbers can range from 0 to 255. So each number can take one of 256 values. And therefore, the total number of available IP addresses will become 256 into 256 into 256 into 256, which is about 4.3 billion. And that looks fairly sizable until you look at what exactly or how big the internet has grown today. Even as of now, there are many billions of mobile phones and billions of computers, and there are tens of billions of IoT devices. So clearly, there is a limit on the number of IPv4 addresses, while the number of actual devices, there's a limit on the number of IPv4 addresses, while the number of devices are growing rapidly. And there aren't enough IPv4 addresses to go around for all the network devices and machines. Right? So one option, like I said, is to take up a different standard, which would be IPv6, which supports a much larger range of addresses. But even today, IPv4 is very popular, and RFC 1918 and this idea of private addresses is for IPv4 only. So what RFC 1918 defines as part of its proposal is that we will allocate a certain set of IPv4 addresses that are going to be completely private. Right? When you say private, it means that if somebody tries to send a packet to it on the public internet, it is not going to pass that through, right? It's going to drop that packet because it says, you know what, this is intended for a private network. So if you find it in the public domain, something wrong with that, right? But if there was a private network and you found this address being used, then that would be completely fine, right? If there's a data packet that is intended for one of these private addresses in a private network, the router will pass that on. And the advantages of this is that the same IPv4 addresses can be used by any number of organizations as long as they use them locally. So for example, I can have a private IP address with a certain I can have a private network with a certain IPv4 address, and some other person also can have their own private network with the same IP address, but obviously these cannot directly communicate. So RFC 1918 says, here are 3 sets of addresses that are allowed to be used in a private network and which won't be routable on the public network. So if you're in a home network, right, typically you're not going to have a large number of devices. So you might end up using this range, which supports about 254 usable unique IPs. This is because the ones on either end are used for other purposes, right? One of them defines a network itself, and the other one is what is called a broadcast address. So even though there are 256 possible, 2 of them are not really usable. And if you have a slightly larger network, you can go for the one that starts with 172.16, which means that you will have about 65,000 unique IPs. And for very large organizations, you can start with a 10 dot address, which has about 16 million unique IPs. So if you're working in large organizations, many of your devices might have a 10 dot address. Now there is no restriction that only large organizations can use the 10 dot address. Even if you want to do this at home, you can do it. But typically, you tend not to do that. You would use one of the other ones, right? One of the smaller networks. You just as a convention, that is what you would be using. So for example, if you're in a small organization, maybe your IP addresses start with 172 something, and if you're at home, it starts with 192.168 something, and that would be expected. So why do we, or how does RFC 19 then manifest itself, right? So if you're looking at the general internet, and you have a home network, you have something as a part of home network, which has a router that is sitting at the endpoint, which is the one that is talking to the internet, right, to the public internet. And that router will essentially have two addresses. One that is facing outside, which would be the public address, and that would be something from the public pool, right? Whereas the inside facing thing, the address would be 192.168.0.0, which defines this whole network. And inside this home now, we can have multiple devices. Say, for example, a mobile phone, maybe a smartwatch, a smart bulb, which is all communicating with this router. Right? So any data that is intended to go outside the private network, it is going to get routed through this and then goes to the public network. Right? So as you can see, there is the IP addresses, which is part of the RFC 19 defined private address range, right? Starting with 192.168, and you can have up to 254 in this set. If there was, say, my neighbor who also wants to have their own private network, you can do that again, right? So even they can repeat the same addresses as part of a local network, provided, of course, there is something at the front end that routes this to the public internet, and that needs to have a public address. So what we essentially get is that even though we've got a limited set of IPv4 addresses, we are able to expand the number of devices that can be on the network by making sure that these are only going to be part of a private network. Okay? And this does not have any kind of routable capability within the public internet itself. So the same thing extends to, as I said, even for larger organizations. If you've got thousands or millions of devices, you would ideally put that in this class of IP addresses starting with 10 dot, and you will have different machines, and each of them will internally have probably the same IP address, right? So this can have a 10.0.0.1. This can also have a 10.0.0.1 without conflicting with each other, right? So the concept of it being unique is local to a private network, and it is not to the entire network. So even with one public address, you also have the ability to bring on a much larger number of devices onto the internet. Now, obviously, this raises a question, right? If these addresses are repeated, right? If there are duplicates, even though they are in different private networks, if they are duplicates, then how do they communicate with each other? So for example, this phone, which has got a 0.3 address, if it wants to send data to a 0.2 address in another private home, how will that work if there is another machine in this local network itself that has got a 0.2 address? So if this phone tries to send it to this AC with 192.168.0.2, it will say, oh, this is locally available, it's going to send the data here itself, right? So you can't directly access a device that is part of another network. So what actually happens in such a situation is that there is something called a network address translation, or NAT, which sits at this point to say anything that comes from 0.3 is going to be repackaged in some way and sent out onto the public internet, and it makes it look like it actually came from the device 100.1.2.3, right? So it masquerades, or it wraps that actual data in some way so that it can be routed on the public internet, so that it goes to another location. And when the data comes back again, it is going to go through the same process where this one is going to mask what was the original address, put it on this, and as far as this machine is saying, it looks like it came from 101.456 and not from 192.168.0.2. So, in summary, then, what RFC 1918 does is to allocate these private addresses that can be repeatedly used by different private networks without conflicting with other machines on the internet. Right? But any data that is intended for that is going to be dropped if it reaches outside the private networks. Right? So, if there is a gateway that says beyond this is the public internet, it just any private address data is dropped right there and doesn't go into the public internet. So this means essentially that any organization can expand their subnetwork and have way more devices, even with just one front end or one public IP address that they have. And this also has a certain amount of security benefit because it hides the information about what is the actual machine that is sending this information, right? And that's one of the considerations we'll see later. Now, why is this important for people coming into Google Cloud? When companies move into Google Cloud, usually they have huge setups, right? It's not always like a couple of machines moving to Google Cloud. They might have a big organization with thousands and thousands of machines, and not all of them are going to go to Google Cloud immediately. Right? It takes some time to do some of these migrations. And in certain other cases, there will be situations where they definitely have to continue having a private data center for regulatory requirements. Right? So maybe a government might say, you can't put this on the public cloud. You have this private data center. You have to necessarily retain your data there. So whether they are in the process of migrating, whether they're halfway through it, or whether they're permanently in two places, they will have the necessity or the need, right? They will have the need, the requirement to ensure that there are two networks that are simultaneously operating. So in this case, company has a private data center and it also has a virtual private cloud within Google Cloud, right? And we need to ensure that the machines within this VPC is able to talk to the machines within the private data center. And in doing this, what we would also like is that the IP addresses that they use also be part of the same shared space, right? Otherwise, as you saw in the earlier case, you will have to constantly be translating between the public address and the internal IP address, right? And just becomes complex and possibly even slow. So we would like to have technologies that allow these machines to talk to each other as if it is in the same physical space, right? As in the same physical space, like say, for example, two parts of the same corporate entity, but they're still addressing each other using these private addresses. So there's no need for it to go to the public internet. There's no need for it to use any kind of translation. It is able to directly talk and address each other. And for this, we would have multiple options within Google Cloud, right? We'd have multiple options in Google Cloud, and there are a few of these that you should check out where this is supported, right? Where this RFC 1918 addressing is supported. So let me just go back on this. So RFC 1918 essentially says we are able to share the same IP addresses in this case, right? If a product supports RFC 1918, that is, it is saying that we are able to share the same IP address space, like 10.001 here, 2 here, 3 here, and 4 here, as if it is part of the same logical network, even though this is completely separate. And obviously, in these networks that share this IPv4 address space, the machines cannot have the same IP, right? Two machines, there can't be one within the Google Cloud VPC that is 10.001 and another one within the private data center that's also 10.001. So that's obviously something you have to take care of. Also, when you're merging networks in some cases, right? Maybe there were two separate private networks, and now for some reason you need to merge those networks so that the engineers can work on that together. In that case, also you need to ensure that there are no conflicts in the after you do the merge. There are multiple products that support RFC 1918 addressing within Google Cloud. So for what are called hybrid networks, right, that work between a private data center and one of the public clouds, in this case Google Cloud, the options are you have a dedicated internet, partner interconnect, and cloud VPN. and this connects hybrid networks. Whereas if you're having two organizations within Google network itself, then you've got something called network peering. So all of these are supporting the RFC 1918, which essentially now means that on two parts of the network you can have private addresses which are within the same range. And of course, to communicate with devices on the internet, these are not going to only communicate within themselves. They'll obviously have a need to communicate with other machines also. At that point, if you put a NAT at the network edge, right, at the endpoint, it will do the translation to ensure that the data can go back and forth, but it still masks the identity of the specific machine that is within this private network. So a machine 10001 is not seen as 10001 outside. Instead, it is seen by the public IP, which is convenient from a security standpoint. If you find these videos useful, consider supporting me on Patreon or buy me a coffee. Also, don't forget to like, share and subscribe for more learning videos on Awesome GCP.